Okay, live stream running. Good morning. Morning, everyone. Sorry for the delay. I noticed the setup of the new live stream didn't work, so I had to create a fresh one. In case you're following from home, we will have found it by now. It is on Campus Wire, but not much help to announce that here now, I guess. Yeah, any news? I didn't get to look at the videos much last week, so that will take some more time. And we'll also have a look at all the Bamboo submissions. Yeah, we have a new continuous assessment, the last one for this module, coming towards the end of the week. So I just wanted to publish this before you go to in the Easter break. There's enough time to work on it outside of the Easter break, but I felt it's useful to throw it out already towards the end of the week, I guess. It will be similar to the Bamboo one in the sense that it's a little puzzle that you can solve outside of the computer if you want, and there's a little piece of code to submit. But there's also ways to solve this in a way more coding heavy, where like for Bamboo, you can come up or find algorithms that work for this in more general sense, and then just use them to produce solutions. Well, you'll see what that one's about. It ties into Unit 8, which we haven't covered, so it's also why it's due later. Yeah, that's the new continuous assessment to come up soon. They have a few days of break from this one at least. What else? Yeah, should be a few more class tests coming as well. I will probably put several out and then leave you a long time over the break for doing them until sometime after the break. Okay, with that, back to compression. Let's have a brief look where we left off, because this is the second part of l'impulsive Welsh. So going all the way back to the introduction, just to bring this again to your memories. It was about this poem, the introduction, where you have references to parts you used earlier. That was the key idea to exploit in all these l'impulsive compression algorithms. And then more concretely, the steps, maybe that's a good way to highlight it here. Each step of the compression consists of finding the longest match from the current position of the text, what you haven't encoded. What's the longest match you can find in your dictionary? That's some substring that occurred earlier. You find the longest such match, encode that in one go, but then after you encoded it, you add a new word to the dictionary, a new phrase, which is what you encoded plus one additional letter. And then this ban A becomes part of the dictionary and becomes available for compressing longer parts for the subsequent stages. And we've gone through this example where you saw this in action. I just wanted to point out that these strings in the dictionary, they get longer and longer, naturally. They don't always get used. Some are just inserted into the dictionary and then you never really touch them. But I wanted to stress here, for example, this your, if you include a code word, a phrase, if you include a phrase of 4 letters, it means at least that the first 3 of that were used earlier, because that was the point when you inserted this one. And that also meant there's another word here, so yo was also used. So you only ever get to long phrases if you repeatedly used some part of that phrase. So seeing these long phrases means there has been some repetition already. Okay. And that was the code for that. Now, where we left off is I showed you how to encode. But a compression method is only useful if we can also decode it again. In this section, we'll look at how to decode a Lemp-Welsh coded text. Question?
Because like you might miss, does that mean that the encoding process can miss sometimes the most efficient way of encoding if it misses some of the really long phrases which get repeated?
Yeah, okay, so the question was, is it possible that this encoding method misses the longest phrases or the best way to compress? I mean, taking your question in the most general sense, it definitely will sometimes miss the best way to compress. Remember this fractal picture where we said the ultimate way of compressing is write a program that produces the image. And this is a problem that's not just expensive to compute, it's utterly impossible to compute with a computer at all. So in that sense, definitely it will miss things. There are ways, there are things that are good about this. We won't talk about this in the lecture, but since you asked, it's kind of an excuse for me to digress a bit. The Lemp-Welsh methods have some properties that are similar to Huffman codes. So they achieve something like Huffman, but in a stronger sense. They can achieve something like kth order empirical entropy. So this is like the entropy we've seen, but you take into account what was before the symbol as well. And that kind of reflects this repetitions. In another way, I think people are still, this is still active research, find something that is like entropy. So you just take the text and you compute some number from the text, and that expresses the compressibility of that text. Again, the ultimate thing would be Kolmogorov complexity, which is out of the question. But some somewhat sensible way of doing this that reflects the type of repetitions you can pick up with schemes like that. There's still no definitive answer to that. It seems to be tough to capture this exactly. If you ask more humbly, there are specific strings where you can show that Lemp-Welsh doesn't do great, and a slight twist of the method does much better. So in that sense, also yes. Maybe that was the question you had in mind, because if you look at some specific examples, you sometimes it jumps at you that you can do slightly better, but it's tougher to make this into a general method then. Yeah, so that's is a good part of the decoding chapter, so I don't want to cut this out. Let's leave this in. It's a good question. Before we come to a little more of discussion how well this works, let's see that we can actually decode what we produce with Lemp-Welsh. As always, decoding is the opposite of encoding, so kind of we just replay what the encoder has done. So the decoder will have to play the same game of growing the dictionary whenever you decoded one phrase. So for the decoder, this looks as follows. You decode a substring y of the text, of the source text, by means of finding it in the dictionary. And after you decoded y, you have to add from the previous phrase a new code word to the dictionary, right? So that's in the picture, this y is the thing you encode now, or decode now. And it points to some earlier occurrence of this substring. So that's one phrase in your dictionary. And after you've decoded y, you still have to do what the encoder would have done, which means add x and then this new symbol c to the dictionary. That's the same steps that the encoder would have done. It's just we have to delay this adding things to the dictionary a bit, because we have to wait to see what y is before we can add this new character to the dictionary. Okay. If we've decoded y, then the first character is this c. I think that's so far clear from the picture. let's see how this works on an example first, and then code will follow. And pay close attention. Okay, so here's a sequence of the code words for phrases in the dictionary. We start the dictionary in the same way as before. So we initialize it with all the characters in the alphabet. So here again, the ASCII characters. This will be a different example, yeah. But the same initialization, so we use the ASCII characters. So the first thing we know, 67 decodes to a C, and that's the first thing we learned. So the source text will appear following down this column. Then we read the next code word, which is 65, so that decodes to an A. So far, so good. And then the second step is add a new phrase to the dictionary. All right, so our Y now is A. We take the first character of Y, it's just A, and we take the previous phrase called X before, which is now just the letter C. And so the new thing we add to the dictionary is CA. All right, let's do one more. 78 is an N. So that's our Y. The first character is still N, it's just a single one, and we take the previous phrase that gives us AN, and we add this to the dictionary. Something to stress here, maybe if you implement this, you wouldn't really store these strings literally. Instead, you make note of the fact that this apart from the last letter, it's a phrase you had before. So you could just store it as one code word and then one new letter. So you don't need to store a long string in case you care about the space for the dictionary here. Okay, one more, then things start slowly getting a bit interesting. So space, and we add after that previous phrase plus the new character to the dictionary. And one more time. And then for the first time, we see a code word used that was not just a single character, but was one of the ones that we added to the dictionary after that. So that's the input. We look it up. The new code starts here. So we find AN is one of the new entries in the dictionary. So we decode that. And now the first character of AN is A. That's our Y0. So we have to add the previous phrase followed by A into the dictionary. Okay? Can it ever happen that what we try to add to the dictionary here is already in the dictionary? Any ideas? Suppose it was possible. So what would happen if BA is already in the dictionary before? It cannot happen. Can someone tell me why? Should have prepared a Slido question for this one.
Setting up the tree to make sure that there's no prefix.
Yeah, you're getting at the right point. I mean, first of all, yes, the decoder can't really know. You have to look at the encoder. And the encoder made sure that you always take the longest match and then add one new character. And now we're replaying the same thing. So if this had been in the dictionary already, then there should have been a longer match before. When B was chosen as the code word by the encoder, it should have chosen BA instead. And the fact that it didn't means it wasn't there. Okay, so this looks like it's all going fine until we arrive at this funny situation. The new code word is 133, and you see this is not in the dictionary yet. So we're kind of stuck because we would like to know what 133 is, but it's the same time this is the time step where we would fill this cell. And this can happen because the encoder is always one step ahead of us. remember, encoder does encode a new phrase and add a new thing to the dictionary. The decoder has to wait with the adding of the new thing to the dictionary until it has seen the next phrase. And so it can happen that because you wait, you need the same phrase right again. So it looks like this is a dead end. And the reason is this one step behind in creating of the dictionary. So putting this in a different way, we want to use a code that we're just building. And there's a very, very specific situation where this can happen. And luckily, we can analyze this situation and solve it because there's only one specific case where this can occur. So here's the situation, indeed the example from before if you followed it through, but try to not read ahead. So these three characters, Y, are not known to us yet. Okay, the decoder is at the stage, it knows X, that was the previous step. Maybe show this one more time. So we know XAN, that's the last thing we decoded. We are at can ban. And then comes this new part, can ban, that's where we are. And then we ask for a phrase that we're just about to fill. Now, when we create this phrase in the encoder, we of course know what this text is. And after we encoded Anna, we add the previous phrase and C. So this Anna here. And you notice it's the same string here. And that's not quite coincidental, because if this thing that you use now, if you create a code word and then use it right away, that must mean that this X here is the same as this here. So the new phrase is the one you just inserted. So the new phrase Y is the same as XC. That's why I put it here below with these green bars indicating these are the same characters. Because the encoder creates a new phrase and then uses it right away. That means it must be the same thing he just inserted. And that also means we know what X and C is because they're copied over. And so in particular, we know that C is the first character of X in this case. And X we do know. That was the previous phrase. It's a little tricky, but the thing is, if you write down all you know, the only potential situation is that the new phrase that you're trying to decode is the one that was just inserted. And so because you know X, you know that the first character of X must be the unknown character C. Okay? So you can actually solve this by getting, in this case, just setting C manually as an exceptional case, and then using that as Y and inserting the phrase in the dictionary after that, like before. Okay, I thought I had the example completed. I guess after that, maybe do that first. So in this case, we decode this by using that X, the previous phrase, has as first character A, and that must be our C. So if we take X and then C, we get ANA. That's Anna. So we can put this both here for the source text, the decoded text, as well as here for the new phrase we want to add to the dictionary. Okay, it might look a bit magic. Spelled out in code, it looks like this. There's not much beyond what I showed you in the example. One thing that we didn't care about in the example is the data structures to represent the dictionary. In this case, the easiest, because you want to access the dictionary by index, you have a code word and you want to look up what that stands for. So we don't use a trie, but instead we just use an array. And the array stores for each code word, it stores what it stands for, which can either be a single character or another phrase followed by one single character. We keep x around for the last phrase. We keep y around for the next thing to decode. K is whatever we would insert to the next free code word, so the next position in the dictionary that is not used yet. Initially, we set this like we initialize the dictionary with all the alphabet symbols, so the next free one is after that. And Q is the code word, so that's the next thing from the coded text. And then we go through all the letters in the coded text. The letters are numbers here. It's an array of code words. It's already split up the bits into code words. We remember what we had in Y before, remember that in X, then we take the next code word. And here, this is the special case. If the code word that we're trying to decode is the same as K, the next free one, then we're in this Anna special case. And in that case, we just set Y to X followed by the first character of X. In any other case, we said Y, we look up what the code word stands for, because then we have it in the dictionary. Then we append this to the output. Y is the decoded text. And then we have to store the new phrase, XC, as a new code word, and X we have remembered, and C is the first character of Y. And because we caught this special case here above, the adding things to dictionary is regular, is the same in both cases. Okay, there's one more line to finish this example off, but that is a regular case, so nothing special to say there. And so that completes that example. Now, before we discuss in more general a bit how well this works, time to wake you up with a slightly unrelated question to this decoding part. This is just about the encoding, if you want. Oh, is it? Thanks. I was wondering why you're so slow this morning. This is a fairly tough question. It means fully understanding the encoding part. And then analyzing it on the spot. So I'm asking for a bit here. Maybe this question is more for me as an excuse to talk about this best case than to really check your understanding. Quite a few more people on the live stream today, which is great that it's used. I wonder if that has any correlation with the nice weather outside, or if there are other things going on. I think I counted to something like 25 the people in live stream plus what we have here. So unless anyone's still busy thinking, let me show the answers first. And there's variety and an interesting peak for this one. The right one is root n. as I said, this is a fairly tricky one, but it's a great excuse to briefly look at this example. As often, well, I don't know. In this case, the single character repeated all over is a best case for compression. That's it's a feature shared by many compression methods, but maybe not all. So I won't promise more than I can. But in this case, it's about as good as it can go. So let's look at our text, and I'll just put a few A's here, and then we'll try to generalize from that. How would encoding work? For now, let's just look at the phrases that the text is split into. Remember, the encoding does this using a dictionary, but really what matters for this question is how many phrases do we get? And so this is just splitting the text up into certain subsegments. The first phrase is just the character A. We look up in the dictionary initially, it contains all the alphabet letters. There's nothing else in there. After that, we insert the previous phrase plus one more character. That's AA. And we find AA. So this is the next phrase. After we found that, we add this phrase plus a new A, which again we will use right away. So this is, if you want the text to practice this weird dead-end situation, this will be always in that case. It's always the phrase we just created that we now use again. And I guess you see the pattern now, right? We take 3 A's for the next one, then we add the fourth, then we use that right away, and so on and so forth. So what you get is something like, it's 1 plus 2 plus 3 plus 4. That is the number of characters we used so far. And what we want is, that's obviously the sum of the first integers. And we want to know, let's say, k phrases. We want to know that, and we want to have that this is at least n, because we need this to cover the entire text. And then you may know that this is very roughly, I can write this in precise notation. This is k squared over 2 as an asymptotic approximation. It's not exactly that, but pretty much. And so if you solve for k, that gives you square root n. It's an interesting little factoid to keep in mind. If you compare it with run length encoding, remember, best case for run length encoding, same text, compresses it down to log n bits, because you just tell the decoder how long the text is. In this case, you don't get log n, you get square root n. That's worse, but still pretty good. For many texts, you won't get that much of a compression. Okay, that as an order of magnitude maybe is useful to keep in mind. What else can we say about Lempelsiff Welsh? First of all, about the implementation, I presented it so that the output is a sequence of code words. You might want to further compress this because the code words probably don't occur equally, so they don't occur with equal frequency. So you might want to add another Huffman code after that, or some other code that can take advantage of this. Or you just write them in binary. As depends a bit. Then what I told you so far is a little, it was a bit of a lie. I said we fix the size of the dictionary as 2 to the d, so that we have d bits for each code word. But if we keep encoding along a longer text, then we run out of space in the dictionary. So we need a rule to do what we do in this case. And there are different sensible options. We can add more bits to the code words to make room. We can also just say, forget the dictionary and start from scratch again. Or, well, scratch means we start from single alphabet symbols and then filling up again. Another option is to trigger this case even before the dictionary is full and have some heuristic that detects when maybe it's a good idea. Why would you maybe want to flush the dictionary earlier? The idea is there's some portions in the text that are similar, and then there's a different portion in the text that has different characteristics. And all of this compression method is using that things you've seen before occur again. And if that's no longer the case, then it's maybe a better idea to forget what you've seen and start again. But this is a gray, wishy-washy area a bit. There's no very clear rule when and how you should do this. So practical implementations like zip, they have some rules for this. Sometimes the dictionary size is a parameter you can specify if you don't just click the default option, but you use some tool that shows those. So often these are things you can play with and you can fine tune it. But for many applications, it doesn't matter too much. In terms of running time, they both can be implemented so that they run in linear time, which is the best you can hope for if you have to read the text. So that's pretty decent. So we like that they're fast. You can apply them in a streaming-like fashion if you have some rule for how the dictionaries are handled if they get full. You can do this in one go, right? It's not like Huffman that you have to scan the text first, count all letter frequencies, and then start coding. You can do this in one go, both encoding and decoding. And that's why this is also used as transport level compression. You can specify this as part of HTTP, that it compresses the payload. And so it has to work in this way. All right, also it achieves good compression for many types of data. You all have used zip, and unless you zip a zip file again, or zip something like an already compressed JPEG image or video, it usually works quite well and gives you some decent compression of, I don't know, 50%. Some downsides is if you have very, very long ranges of repetitions. So you have a huge text file which is copied twice, say as a hypothetical scenario. If that is too big for the dictionary to contain everything, it might get flushed and you don't recognize this repetition. That's inherent in this method in a sense, because you will run out of space for the dictionary eventually, or you will get some hit. If you increment D, you don't run out of space, but your code words get longer. That's also somehow wasteful. Yeah, so let me point out that the no free lunch theorem that I promised you for last week is on this week's tutorial. It's always confusing because I'm thinking about the next tutorial that I'm putting up, not the one that you're already working on. So this is up on the website now, and you'll discuss this with Ben this week. There's a nice little theorem that proves compression cannot always work. I mentioned this a couple of times. Yeah, but by and large, this is still a method of high practicality and is used in many places. And here's a quick overview of where the different compression methods that we've seen are used or where they're good for. And this summarizes just the summary slides of the previous section, so I don't want to go over this in more detail. It's kind of a service to you to not look it up on the other slides. Okay. Yeah, let me do the first part of this before we do a break. I have a third part in the compression chapter for you, which is about text transforms. And these are a bit weird at first because they're not compression methods by themselves, but they somehow make text more compressible without compressing themselves. So they just bring things that compression methods cannot use right away to the surface so that they can be used. And we'll see some two examples of this that nicely highlight this. It's just yeah, a curiosity that the compression methods cannot do this right away, but there's effective ways around that. If we look again at the 3 big compression methods we looked at so far, that was run length encoding, Huffman coding, and Lemplesif-Welsh. Then you see they have some things that they like and that where they are really effective. Run length encoding, as the name says, if you have long runs, repetitions of the same character. Huffman is good if there are some characters that are much more frequent than others, or vice versa, if there's some characters that are much less frequent than others. And Lemplesif-Welsh is good for picking up exact repetitions, right? So that's the positive things. There's many things where it is frustratingly ineffective to use the compression methods we've just seen as they are. Even though, as a human, if you look at it, you see there is something going on in terms of repetition that you would like to capture. A simple example for Lamplessive Welsh is what I mentioned before. If you have an exact copy from very far ago, then you might not find it just because the dictionary is just not big enough. And keeping the dictionary growing has downsides too. So the solution is not just to keep the dictionary growing. We might want a fundamentally different way to approach these long distance repetitions. Huffman coding, the way we did it, suppose the first half of the text is all A's and the second half of the text is all B's. Huffman would still say use 1 bit per character, and then the compressed text would essentially look the same as the source text. Whereas obviously, something like run length encoding would work well in this case. If you have something slightly less artificial, in the first half of the text, A's are much more frequent than B's, but it's still not quite all A's. And the second half, the other way around, B's are much more frequent. It still feels like you want to compress this better than what Huffman would do by averaging all the frequencies and not compressing at all. But it's not completely obvious how to do this. And well, run length encoding, of course, in the way we presented it is so limited that there's many ways you can imagine to trick it into not finding some repetitions. So text transformations try to bring out these features so that they are compressible with the other methods to exploit such types of repetitions. So they're called transformations because they take the source text and produce some coded text, and they have to be invertible, but by themselves they don't achieve compression. And so they're usually used as part of a bigger pipeline. You first feed your source text through some transforms and then through some compression. And for the decoding, it's the opposite, right? You always have to go back the same way as you came in encoding. The first example of a transformation is called the move to front transformation. It's in principle a fairly simple transformation, and it might not seem very useful at first sight, but it's historically the one that, combined with the second one, gives you the most effective compression for English language text and some other types of inputs. So let's have a look at this. Who has seen the move to front heuristic for self-adjusting linear lists? It's a topic that sometimes appears in some data structure classes, often to introduce competitive analysis in online algorithms, but it's maybe not so standard to cover it even in CS undergrads. So has anyone seen it? Okay. It's only vaguely related to that, so we don't really have to get into that. The idea is you keep a linked list of some objects, and it's not sorted, this list. And so let's do a small example maybe. Okay, I have space down here. I'll just do this with letters. And say this is null. So it's just 3 elements in my list. Now, when I want to access an element, I traverse from the start. So that's the start. That's where I always begin my search. I go through the list until I have found the element. And after that, I make that element the first element in the list. So if we access Z, we go through the list until we find Z. And then we take it out of the list. Remember, in a linked list, you can take elements out by just rewiring pointers. So this is a cheap operation to put. Well, I can, if you want, I can keep this in the same layout, then it's closer to what the algorithm would do. So you make the start point to Z, then that points to the old beginning of the list, and Y now points to null. So I've just taken Z and put it at the front of the list, not changing the relative order of anything else. Okay, that's what's spelled out in the text here. And you keep doing like this. When I do the next access, maybe that's to Z again, then I find it at the first position. And if I then access say X, then I would swap X and Z. So the idea in this is, over time, if you keep accessing elements like this, those that have been accessed frequently or those that have been accessed lately, they end up in the beginning of the list, and so you get cheap access to them, because the time to traverse through the list, of course, is the same as the number of elements you visit. And so if you've seen something just before, then it's at the front, and if not, then it's a little further in the list. But they're roughly ordered by the least access, the last access to them. So it's a way to somehow learn access patterns without explicitly doing anything. It's just following this heuristic. That's the move to front heuristic, because of the obvious property. If you access something, you put it at the front. Good. We'll just use this and apply it on the alphabet characters of our text and basically see what happens. So here our list contains all the symbols in the alphabet. You have to initially sort them somehow, so we'll start with alphabetic order initially. To access, to encode a character of the source text now, we access that element in the list. And to encode it, we write down its position in the list. So the number of elements we had to follow. And after that, we apply the move to front heuristic. So what this means is if you access a character more often, it will get smaller numbers, right? The code words here are just integers. It's one of the examples where we don't go to binary right away. But remember, move to front by itself doesn't really compress well. So this is the first step in a pipeline anyways. And so let's see an example where we can point out this property. Yeah, before that, I wanted to see if you understood the rule. So pretend you have X, Y, Z, A, B, C in your list initially, and then you access A. What does the list look like after that? Okay, looks good. Give you a second to vote, but seems that one was doable. And well, you can still cast your vote, but let me continue because it seems easy enough. So if we access A, we have to move from the front till we find A, and then we just take it out and put it at the beginning. So we have A, and then followed by the rest, just with A removed from that list. Okay? Oh, you don't see it. You did see it. All good then? Did I make any silly mistakes? Looks okay to me. Good. So that's the rule. And this time, because it's simple enough, here's the code first. We'll do a tiny example afterwards. But maybe I'll zip through quickly on that one. In coding, you start with the list containing the letters in alphabetic order. Start with the empty the empty string for the coded text, and then you go through each of the letters, you find it. Oh, sorry, you find the next character in the text. Then you find the position of that character in the move to front list. That's the position P. That is your code word. And then you move C to the front of the list. I didn't spell out the code for that, but I guess you could imagine how to do that. I wanted to point out, in this case, how very parallel the encoding and decoding is. So the decoding does the same. It starts with the list in sorted order. It starts with the empty source text. That's what it produces. But then it iterates through all the positions in the coded text. And now instead of finding a character, it finds the position. So it jumps to position P in the move to front list and gets the character from there. And then outputs that, and then does the same move to front step. Okay? Of course, it's important that they do this nicely in lockstep. Otherwise, we wouldn't decode to the same thing that we started with. And so I want to run through a quick example, not to show the procedure again, but to show you an example of what happens if you do this transformation. So relatively quickly, we find I in the list. We start with the whole alphabet in sorted order. We find I, it's at position 8, so that's what we put out. And then we have to move I to the beginning and move the rest over. So you see I is at the beginning, then there's A, B, C, D, E, and between H and J, where I was before, this is gone. Okay. Next character, N, we find at position 13. So that's our output, and N has to move to the beginning. And then that's what you're left with. So N is here, I is here, and then all the others. And between M and O, N is missing. Next character is an E, so we find this at position 6. That's our output, and then E goes to the front, and so on and so forth. I think it's kind of clear how this works. So let me jump through this more quickly now. Okay, here's the final result. And let's spend a second to ponder over what happens during this encoding, what happens with this transformation. Instead of letters, we have numbers now. That's obvious. What is if we have a run of the same character in the source text, for example, here, FF, what does that translate to in the coded text? Now, yeah, it would have been nice to properly align these two things. As you can see, the second F becomes a 0. And of course, it has to, because after F has been accessed, it's at the beginning of the move to front list. And so next time it's used, it's at position 0. So runs of the same symbol repeated several times in the source gives you a run of zeros in the coded text, except for the first occurrence. And now the other way around, what if we have something funny like these repeated characters in the coded text, the 3 3s? What could that mean? Well, it's the characters here. And maybe you can visually spot that there's another occurrence of this string. And if you check, this is exactly 3 characters ago, or 4 if we start counting at 0. Okay, so if you go back by index, there's 3 things in between. And so that's another general thing. You get these runs in the output if you had a repeated string in the input. And that feels like something useful for compression. That was something a bit like Lample-Sif, where we tried to do these things as well. It's a little more limited if between the 2 occurrences there are other occurrences of the same letters. The nice run gets a bit destroyed. Then you get numbers that are smaller than the 3. in between. If there was between the CIE, if there was another E, then we wouldn't get a 3 here. But it at least gives you some hint, some intuition what might be going on there. Okay, as I said before, it doesn't compress by itself, but because of these two properties, it sometimes can bring out compressibility that's otherwise hidden. If you wanted to encode the code words, you have to think about that, but you usually put some other things after it. The key application of move to front, at least historically, comes from after another transform, and that's the one I want to look at next. And yeah, different options how to encode the code words. I don't want to get too much into the details of that. All right, time for a little break, and then we'll do the most exciting transformation.
then I can feed that back into the feed that back into the and what did it decode? And see how it No. If you look at the data sets, they will bring new connections. Yeah. That's the main thing. Only has two. If it only has two, you can plot it on so then you can see the I'm using that whilst making the signals.
Okay, I think time to continue. I don't want to lose the time for this exciting last transformation. I think it's really cool because if you see it for the first time, it's hard to believe it is invertible at all. And then it takes you another few moments to ponder about why this on Earth should be useful. I will definitely convince you of the first thing because we'll see how to decode it. And for the second one, it's a little tougher. I will point out some observations, and there's some really tricky formal proofs of this as well that we won't cover though. So without much further ado, in the next section of our compression chapter, we'll look at the Bwt Transform. And is one of these things that look really magic at first sight and unclear how they could help. And then over the time, people found that this is a really, really key step to bringing compression to the next level and also putting it on some more principled legs. All right, let me show you what it is. First of all, the Bwt Transform is just a permutation of the letters. So you're given a text and then you jumble the letters around and that becomes the transform. But it's a specific way of doing that, okay? It's not just randomly throwing the letters around. And it happens to be that the output text is much more compressible traditionally by putting the move to front heuristic after the Bwt. But there's many other ways to see why it has compressibility features. The slight downside, and yeah, maybe I can give this historical anecdote as well. It needs the whole text to apply this transformation. You can't do it easily in a streaming fashion. So in practice, it's often applied to some block of data, but in principle, you can do it for the entire text. You just need enough memory. This also meant that at the time when this was thought of, when it was invented by Wheeler, he thought, that's a cute idea, but it's completely useless because it's impractical to do. He thought there's no way that we'll ever have enough main memory to make use of that compression technique, so he ditched it. And later, when he had, I think his student, Burroughs, he explained that idea again to him. That was then in the mid-90s, and he said, yeah, let's implement this. This should work fine. And it did, at least shortly after that. And it's still using the same memory so there were no theoretical improvements on the idea at that stage, but it became practical because the machines got a little bigger and a bit faster. So it used to be something that people believed is just of curiosity, of academic interest, and a curious algorithm. But then it turned into something practical, and now it's at the heart of pretty much all genome-wide analysis to use something like this transform on really huge data. So it's a nice illustration that sometimes things don't seem practical right now, but often that's only a statement for a certain time, and it can change. As data becomes more big, becomes bigger and bigger, asymptopia comes closer to us in this sense. Okay, but back to the more concrete topic. The Bwt became famous for being part of this bzip program. If you have a Unix system where you use the departmental ones, it will usually be installed. It's just bzip as a program, bzip2. It's not as well known as I think it should be. If you take the ASCII text of the Bible, by the way, it's 4 million characters is pretty much the text of the Bible in English. And you can compress this with, well, gzip is some implementation of the zip algorithm. Gets down to a quarter of that. 7-zip, this may be more well known. Well, hack combining many different heuristics gets it further down, but bzip is even better than that, and that's typical for natural language text. It is slower than gzip by many orders of magnitude, I think, but still fast enough to do on large inputs. So what is the Bwt now? That's 2 T's. The Bwt transform is the Bwt transform. It is based on the notion of cyclic shifts. If you have a text, then imagine you write it on a circle. Then there's a certain point where the text begins and ends. And a cyclic shift is you just put this divider somewhere else. And I tried really hard to find a string where you can do a cyclic shift and it still is a correct English sentence. Even though maybe not a great one. So that's a cyclic shift, right? Every position where you could potentially put this separation between start and end gives you a different cyclic shift. Now, in general, you could have a string where there are not as many cyclic shifts that are different as there are positions, just because 2 of them are the same. To avoid that situation, as we've done many times before, we always throw this end of word marker at the end of the string, pretending that $ is some symbol that doesn't occur anywhere else. That means we can always recover the original string from the cyclic shift. We just have to look for the $ and put the cut right after that. So far, so easy. The Bwt transform now does 3 things, and this is the conceptual view. I will present you how you should think about this. This is not the way you want to implement it, because that would be awfully slow. But let's first understand what it is. You write down all the cyclic shifts of your text, one below the other. That gives you a matrix of characters. I'll have an example on the next slide. Then you sort these strings lexicographically. So you sort all the cyclic shifts lexicographically. And then the last column is the Bwt. So again, on an example, we have this text, Alf eats alfalfa. Again, as a brilliant example, because it has lots of repetition. And in case you haven't heard this before, alfalfa is some sort of grain. I mean, it's a real thing to eat. Whether Alf would like it. So you write down all the cyclic shifts, and you can see how the $ makes its journey all the way to the front. Right? That's how you can easily see that you got everything. But this is just all the cyclic shifts. What we want to do next is sort them lexicographically. So that gives you that list. Okay. And as before, we'll treat the $ symbol to be smaller than all the other characters. Then space. This is like in ASCII, space is before the letters. Then come the A's, E's, F's, L's, and so on. And where there's a tie, you go to the next character. You know what lexicographic means, I guess. So this is a well-defined step. And now the Bwt is take the last column and read these letters top to bottom. So from Alf eats alfalfa, what you get is this permutation of the letters. And you may note, or you may count, that there's $1 here, $1 here. There's a whole bunch of A's over there, and they occur as well down there. It's the same number, they just get shuffled around. Already on this tiny example, you can see there are things going on with runs. There's 3 L's and 3 A's in a row. That's not coincidental. It's one feature of the Bwt that you tend to see repeated runs of one character, the same character repeated several times. Before we dive deeper, let's think about whether you've seen something similar before. And that's this question. Maybe superficially you recognized we put end of word markers and there's some sorting going on. So that should ring a big bell about suffix arrays. But the precise statement is a little tricky, so have a quick think about this. Okay, we had 30 people voting before, so I'll probably have to leave this open a bit. Okay, 25, let me show it for now. And so here's your answers. And the right one is really B. There's some truth in saying both A and B, but that needs some extra tricks at least. So that's why I put this easily here. And I think if you say very easily for the first part, then it's justifiable to say that's wrong. Let me show you, though, what is doable, namely the other direction. How could we compute the Bwt? So what we don't want to do is write down all these as literal strings and then sort them. That would be at least quadratic, just to write down all these characters, quadratic in the length of the text. And that's where we already walk away and say, no, come on, that's not good enough for us. But we can do better. We may note that these cyclic shifts are essentially the suffixes of the string. I grayed out the characters after the $sign here, which is just visible maybe. And if you think about it, if you compare two of these cyclic shifts in a lexicographic way, you will never compare beyond the $symbol because they're cyclic shifts. So the $symbol is at a different position in each of the lines. And as soon as you compare the $, you will have resolved all ties, even if the rest of the text is the same character repeated. You never compare beyond the $symbol. So you will never need these gray characters to decide any ordering questions. So in a sense, I could have just removed the gray characters and I would get the same sorted order on the right. That's the first observation. So we could get, with the suffix array, we could get, where do I have to start with my cyclic shift? So the 16 here means I start at position 16, the last character in the text, and then read from there, and so on and so forth. And now, how do I get this last column? That's why it's convenient in the Bwt to add the entire matrix of characters, so we can just say, take the last column. But it's a cyclic shift, right? So if I go forward to the right, I go left and wrap around if I go to the previous character compared to the first one. So if I know that the cyclic shift starts at 16, what's in the last column is 16 and whatever comes before that, so 15. And the 15th character in the text is an A. So you can always do this, and that's what's written here. The ith character in the Bwt is, if you take the suffix array and for position I, subtract 1, because we want to go one character before, and then take the position at the text. You have to take care of the wraparound. If you have the 0, then you have this extra special case, but the rest is regular. Okay, so this is in a sense, you can very easily compute the Bwt if you are given the suffix array. Now, if you've already learned how to compute the suffix array, that direction is fine. So we can compute the Bwt in linear time. Okay, so it's a good transform. It's relatively quick to compute it, even though more tricky than move to front, to be fair. Now, why is this transformation any good? Because we sort, what happens is that in the sorted order, same things are grouped. For example, you have here a lot of A's in this text. In the first column, they have to be all together because it's sorted by these strings. So all the characters, all the first column is just the characters in sorted order. And then what is going on in the last column means that this A is what comes before this, what comes after this F. So you have a context A that is fixed, and then you look at, in the Bwt, what are the characters that come before this A? Well, more generally, you can have several characters, like LF appears 3 times. If you look in the text, LF, 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 and the character before this LF is always A. And that's why you get 3 A's in the Bwt right here. All these A's are followed by LF, and the LFs mean they are grouped together. So in a sense, what the Bwt achieves is it groups characters by their context, what follows them in the text. And if there's a character followed by the same things, then it will appear as a cluster. And these local clusters of some characters being much more likely than others, this is what then is picked up by the move to front heuristic. That will mean that the move to front output has mostly small numbers in a vague sense. And the other way around, if you have a repeated substring in S, some exact repetition of a string, that inevitably means there's repeated runs in the Bwt. That's the example of LF, for example. The repeated string is ALF. And if you take the first one off, LF is grouped together by the sorting, and so all these A's are lumped together. Okay? Somewhat magic, but that's the essential property. This part is what really makes the output of the Bwt more compressible. To show this in action, here's a bigger example. So this is this bigger text, and here's its Bwt. You see the matrices up here. And then I also applied the move to front to this one. And I think we'll discuss this at the end. All right, let's do it. There's another slightly tricky question. I do want to show you how to decode this, so maybe let's just do this let's do this quickly. The runs of H is, so there's this long run of H here. which of course in the move to front then gets to a run of zeros. What can we say? Where does this run come from? I think the okay, in the interest of time, let me show you the results that you gave. There's several statements in the list of options that make some sense. The very concrete thing that we can say for this run here is, if you look in the first column, there's all these A's. Now these happen to be all A's in the text, okay? In the first column, they are all together, and these are all the A's, which correspond to all H's in the last column. So what does that mean? It means all A's are preceded by an H in this text. So whenever I see an A in the text, the character before it was an H. That's why we get this long run of H's. In this concrete text, that's the most precise statement we can make. It's also a little bit of an anomalous text because it has this strong property that every A is preceded by an H. If you have something slightly weaker, then you might not get one uninterrupted run of H, but you might get a long run of the same character, maybe with a few other characters sprinkled in. So that's why this is the right thing. The first one doesn't really explain the run in the last column. This one is the opposite. It's the context in the other direction. So what the Bwt gives us is the things that come before H. It's a little unintuitive, maybe. So these two things look in the wrong direction. And H is always followed by A is similar, but again, the real statement here is this other one. To finish off the compression chapter, after a long go, I know, let's have a look at how you can invert the Bwt. I've shown you how to compute it. We've seen how to efficiently compute it. And I gave you some intuition, this grouping by context, why it makes compression effective. But from the definition, it's not at all clear that you can decode it at all, because after all, you sort it. Normally, if you sort a list of things, then the original order is lost. And in particular, had I chosen the first column of this matrix, then I wouldn't be able to invert it. The first column is just all the characters in sorted order. Once I've done that, I have no way to go back to the original text. But the Bwt can be inverted. And that's a remarkable property. Before we discuss how this works, I'll just show you the algorithm. I'll show you on an example how it works, and here's spelled out a bit more cleanly how to do it. So we have an example, that's the Bwt. Now I write down the Bwt here in the first component of a pair, and the second component is just the index in the Bwt. Okay, so index 0 is an A, index 1 is an R, index 2 is a D, and so on. That's what I work with. And now I sort these pairs lexicographically, if you want again. I sort them first by the character, and I break ties by the second position. And that's the list we'll use for decoding. So there's another sorting step, but it has to be a very specific one. As I explained, you have to sort by the characters first and then by the index in the Bwt. That will mean always the first of these pairs has a $. And now we'll do the following steps. We'll use the second position like a next pointer in a linked list. We start with the $, and we follow its next pointer. And whenever we enter a pair with the next pointer, we write out the character that we see in the first column, first position. So this one has an index 3, so we jump to 3, and A is the first output. Then we take the index from there and use it as a next pointer. So 7 leads us to this down here, puts a B out. And we go from there to 11, so we find an R, then 4 brings us to A, and so on and so forth. So you run through the text, always just taking this one as the next index to visit. And magically, abracadabra, you end up with the original text. And you know when to stop because you've reached the first thing again, or you've reached the $ symbol again. Either works. Okay? I think the algorithm is very easy to follow. If I gave you this example and told you another time how to do this, or you have a look at this, you would be able to reproduce this by hand quite easily. But it seems completely unclear why this is the right thing to do. So what we need to do this, if you analyze the running time, we need to sort. And we sort pairs, so that's 2 rounds of counting sort, because the first one is from an alphabet, so that's small integers. The second one is integers. That's all fine. So you can use this black box from Unit 3. But why is this the right thing to do? These are the steps we have to follow, but I want the example on the slide. The decoding works character by character. There's only one thing really to get started, and that's the $sign. That's only occurring once, so that's somehow easy to find. So in the Bwt, we can find the $. Symbol. That's easy. Now, what is the first character in the text? It's whatever follows the $sign in the wraparound. So we would like to know, if I'm in this position, how can I jump to the first character, the character in the first column of the same row? That's this first step. And for that, all we need is all the characters in sorted order. If we had a list of all the characters in the Bwt in sorted order, then we can jump there because we're in position I, and so we just take the ith character in sorted order. Okay? These are sorted. If I know an index, I can jump there. And in a way, what we did in the algorithm is reproduce the sorted list of the characters. So that's step 1. If I know a position, I can jump to the character in the first column. The second step is to continue. That gives me the first character, B. Now, how do I find where to continue? I have to use these, I have to somehow jump to the next character. And so what you can do here is illustrated one step later if you have all these A's. Remember, all A's appear here together because they're sorted. And if you follow where they come from, just from looking at which A in the word it is, they appear in the same order. They're the first, second, third, fourth, first, second, third, fourth. The relative order doesn't change. And that's a property of the Bwt again, because you sorted these texts. If what comes here after this was earlier in the alphabet, after the A, then after you cut away the A, ban is also before N, N, N. So ban is before N, N, N. So this A must come before all the other A's. Okay? So how do you exploit this? You find your B, and now you count how manyth B is this? It's not the first, it's the second B. And so you walk down your Bwt, and you also find not the first, but the second B. So that's the next step. And then you do the same thing again. You jump into the first column using the index in the sorted list. And you find this is the fourth A. So you go to the fourth A in the Bwt. And that's how you jump from left to right repeatedly and get one character out each time. All right. That's the Bwt. So we've seen decoding is much easier, actually. It doesn't need fancy suffix sorting. It just needs counting sort and following these imaginary pointers. But both are overall linear time if you just look at the theta class. It's typically a bit slower than other methods, but computers have become fast enough that it's very competitive. And if you wait a millisecond for your zip file to email it to your friend, or you wait half a second, it doesn't matter much. It doesn't need access to the entire text, so it can't be used in a streaming fashion, but you could apply it to blocks. That's a hack to go. The bzip2 algorithm, because I haven't pointed this out, it uses first the Bwt, then move to front, then run length encoding, and then a Huffman code for what comes out of that. That's pretty much the compression method you've seen. And that's still among the best we have. There are more principled choices by now that actually get the same performance and are a bit cleaner to understand. I wish we had some more time to go through that, but I think the module is full enough. And this session has been full enough. So yes, just the update of the comparison. These are the 3 compression methods we've had, and we added the 2 transforms. And yeah, we'll leave it with that. There's still interesting things happening in compression. So a lot of what we touched on is still active research. So I like this topic a lot. But then we'll leave compression with that as well. Good. See you on Thursday with some updates on the new continuous assessment and a short unit that we might actually finish on Thursday.